Hi, I hope everyone's doing well today. So what we're going to talk about today is magnetic induction, or I should say electromagnetic induction. Um, so let's go ahead and get into it. We've seen before that that a moving charge generates a magnetic field, but is it possible for a magnetic field to generate a moving charge? Yes. So it can work backwards. Um, so a changing magnetic field, and it can be changing in direction or strength, um, creates um, an EMF in a conductive material. So this is electromagnetic induction. This property, that a changing magnetic field can create an EMF, this is known as like Faraday's law. After the guy who discovered it, although I believe another guy, Maxwell, did the math on that. Okay, so we've got this process where you have a changing magnetic field creating an EMF in a conductive material. But now, what is that EMF going to do? Okay, so now we have an EMF. Well, an EMF once you've established an electromotor force or a voltage, right? Once you've established a voltage, will generate a current. Okay? So now you've got this current, and what's going to happen is this current that's generated will be, or let me just say this. So we'll generate a current, and then this current, because it's a current, then generates its own magnetic field. Okay? So it kind of comes full circle. So you've got a changing magnetic field that creates a voltage. That voltage generates a current. That current then generates its own magnetic field. And you must be wondering, okay, so now we've got another magnetic field. What's that do? This magnetic field is such, this new B field is such that it seeks to, what's the word I'm looking for? Stop the changing original B field. So basically what happens is this current generates its own magnetic field. So this current is in a direction that generates a B field that's kind of opposite to the original. Or it doesn't have to be opposite to the original. All it has to do is be in a direction that seeks to stop the changing B field so that it doesn't change anymore. And it does this so that it can return to equilibrium. So this is so can return to equilibrium. Okay? So everything in the universe wants to do this. Everything wants to be in a state of not changing anymore. They want to be in the lowest energy state possible. So if you've got this changing B field that's creating a voltage, that's creating moving charge, that's higher energy. And so basically what happens is this physical process is created that, known as electromagnetic induction, that stops that. Okay? Um, so basically, the definition then of electromagnetic induction is the physical process where a changing magnetic field produces an EMF. Okay. And so, like I said, you've created an EMF in a conductive material, and that generates a current. That current generates its own field, and that new B field seeks to stop the original changing B field. The current, its direction, that is known as Lenz's law. So we've talked about how this was Faraday's law, but Lenz's law gives you the direction. So Lenz's law says that the current generated from induction is in a direction such that the new field, let me be more specific, such that the new B field created is in the is in the direction necessary, because it's not always opposite, and I'll show you what I mean by that, is in the direction necessary to stop the changing original B field. Okay? So, let's go ahead and give you the formula for this stuff. So here's the symbol. This represents EMF, right? You may remember it from when we did circuits. It's script E. And what it looks like is basically this, where this, and I'll talk about what this is kind of a representation of the magnetic field on the surface of the conductor. So this is called magnetic flux. And I'll talk about what this is. This is changing time, right? So it's the changing field over the conductor over changing time. And this is because of Lenz's law. This negative sign contributes to that. So we've got this formula. Let's talk about first of all, what magnetic flux is. So magnetic flux is, in a way, is the magnetic field, but it's the magnetic field through a surface. So magnetic flux is the magnetic field through an area for 2D and surface for 3D. We might have talked about flux before when we were talking about electric field, because you can have electric flux. But basically, it's any sort of vector field that can go through an area in 2D, like this circle. So this would be your area A. This would be your field. Area in 2D, and then surface if you're talking about 3 dimensions. And it's got the symbol phi, or capital Phi, okay? Kind of like the Green Lantern symbol. And then you add your subscript for what you're talking about. So B for magnetic field. If we're talking about electric flux, it would be E. Other types of flux probably have their own notation associated with it. But basically anything that's a vector field, which is like any sort of field that has a direction to it, so electric field, magnetic field, whatever, they'll have flux associated with it. So this then, magnetic flux, so that's the symbol for it, so that's phi. And it's equal to the field, and because we're going to be doing just 2D, the field that's perpendicular to an area A. Okay, so this is perpendicular. I'll just write it up. Perpendicular. So this equals BA cosine theta. So this is going to be the area or rather the angle between B and A, because we want the amount perpendicular to it. So if we were looking, we have our thing, and we were, oh, that's a really bad circle. And we were like, we had a field going through it, and this field had an angle theta. If we wanted the flux through this area, if we knew the area of this circle, and we knew the flux, we could just plug that in, and we would be set. And you'll see when we do examples like this that that's how that works. So the changing flux through an area. So if we're doing, you'll see examples where we have like a magnetic ring, or a magnetic ring, like a conductive ring. So it'll be like conductive. And we'll have a changing field through this. And we'll see the current direction of this will be such that it stops whatever's occurring, whether it's the magnetic field, the ring moving through a magnetic field, or maybe it will be the magnetic field itself is changing, like reducing in intensity, or maybe it's changing direction. And it will induce a current either this way or in the other direction around this ring to generate its own field. And I'll show you how to do that when we do examples. But it's not too bad as far as the math. Like, it's just this equation and then this one so far. Okay. There is one more equation. If you have something like a slinky or something with multiple turns, you can adapt this equation to include that, where it's just the number, well, technically here, let me do it this way, where it's just the number, or hold on. Where it's just the number of turns added to it. And then it's the same equation, so you would write it like this. And then you'd put a little delta symbol probably right there. Because both B and A can be changing in this instance, or the angle can be changing too. You can have a moving ring that's rotating. Okay, we won't do stuff like that because that's a little bit advanced, but you know, there is one other system I want to look at. So this is one equation. So, and we're really only going to look at one system. So we're not going to do anything with inductors, which is a circuit component that takes advantage of this physical property, but we're actually not going to do anything with inductors. But one system we will look at is basically we're going to have, so this is going to be all conductive, okay? and we're going to have a bar of conductive material moving in a direction and moving at a rate of velocity v, so it's moving in this direction. This will be some length L, and then there will be a B field in here in some direction, either out or into the page as it is right now. And the EMF generated from this system will be BLV, like that. So, like I said, that's kind of the types of problems that we're going to look at. We're really going to look at this system. We're going to look at this system. And then we're going to do like a problem where I show you just how to do a problem just about flux, like what's the flux through an area. And so so the last thing with induction, because these are just numbers, right? So I'm basically going to ask you what's the magnitude of the EMF created and what the direction is when we do these sort of problems. Similar to like when we were doing magnetic field questions, and it was like, what's the magnitude of the field created and what's the direction of the field created. So field plus direction, in this case, current plus direction. So we're going to want to know what is, or how do you determine direction of current. And it's not always opposite. So it won't always be a field that's opposite to the field that currently exists. That's sometimes the case, but often people get confused, me too when I was learning it, that the field isn't always opposite. It's sometimes the same direction of the field, because sometimes the same direction of the field produces a current that finishes the change as fast as possible. It's basically the fastest path to getting back to equilibrium. And so sometimes the field will be in the same direction because of that. So if the flux is decreasing, so if, like, for example, the area is going down, then the B field created by, it's a really bad Y, by the current will be in the same direction as the already established B field. Okay, so this is the case where it will be in the same direction. If the flux is increasing, i.e. area going up, or maybe the magnetic field's going up, just the flux needs to be increasing, then the current will generate the opposite B field. Okay? And as before, you're going to be doing the right-hand rule for this. In this case, you're going to be doing the one where it's just thumb in the direction of current, and then the curling of the fingers will be where it's at. So you'll have basically, like on this instance right here, you'll be curling kind of like here. Because we're increasing it, right? So we're increasing the area, the flux is increasing, so this would generate it in this direction to the right to generate a field that's going out. And so this would be in this instance, it would be a counterclockwise. But I'll talk about that when we do examples, okay? So you have to have a good handle on the right-hand rule to be able to do this, or be able to do cross products really well. and I'll show you what to do there in the next video. So thanks for watching.